Welcome to Unit 2. This is Newton's Law of Motion. And today we've got some great problems picked out. And let's go over some preliminaries before we get started. Alright, so if the net force exerted on an object is 0, then the acceleration is 0. So the velocity is constant. And the one thing that always gets confusing is that velocity is constant. That doesn't mean that the velocity is 0. The velocity could be like 10, right? But as long as the velocity doesn't vary with time, the acceleration, which is the derivative of velocity with respect to time, is 0. And if the net force exerted on an object is 0, we say that it is in equilibrium. And there's multiple types of forces. There's contact forces, which is like friction, or like friction is the main example that we look at here. And we also have field forces like gravity, electromagnetic force, which will be next semester. And forces are vectors. So a force is a vector, meaning that it has multiple dimensions. And oftentimes we're going to separate the force out, into the x and y components and analyze them separately and then come up with an answer. And another thing is that mass is different from weight. So weight is a force and it changes with gravity. So remember that the weight, which is a force due to gravity, is equal to mg. It's equal to mass times your gravitational acceleration constant. Cool. Alright, so just some review of Newton's laws. We've seen this before. Newton's first law of motion. When the acceleration of an object is 0, the object is in a state of equilibrium, and the sum of all of the forces in all directions is 0. So if there's no force, there's 0 acceleration. There's the net force, if it's 0, there's no acceleration. Newton's second law of motion, F equals ma. The acceleration of an object is directly proportional to the force acting on it. And this is what we're going to apply almost all the time. And remember, acceleration is a vector here as well as force. So if we're looking at acceleration in the x direction, then we should look at the forces also in the x direction. And Newton's third law, which is for two objects interacting, the force exerted by one is equal in magnitude in opposite direction to the force exerted by the other. So a classic example of this is just a box, right, sitting on a table here, where you can imagine it's actually sitting on the table here, and you can imagine that the weight of the box exerts a downward force on the table, and then the table will exert an upward force on the box called a normal force. And this is two objects that are interacting. The net force is 0 because there's no motion. So that's Newton's first law, right? There's no sum of all forces is 0. There's no net acceleration. And Newton's third law, which is saying equal and opposite reactions. All right, so some special types of forces. So frictional force. There's two flavors of frictional force. There's static and kinetic. So static meaning kind of at rest. It's the force to overcome basically an object at rest, versus kinetic, which is kind of a friction that's dealing with an object that's in motion. So like friction itself is kind of like, you can imagine surfaces as being rough here. And if you have a box that's sitting on a surface, so like imagine this is like grass, or imagine it's just like dirt or ice, for example. And I want to think about it. Is it harder to pull the box when the box is already at rest? So if you imagine a guy over here and he has to pull the box, is it easier to pull the box if it's at rest, or if the box is already in motion? Well, I would think it's easier to pull it if it's already in motion. And that's kind of how you can remember that the coefficient of static friction is higher. It's harder to pull an object that's already at rest. It takes more force to overcome the static friction. And so generally we look at the maximum value. So this is the equation, so the force due to static friction. is less than or equal to the normal force times the coefficient of static friction. And yeah, generally we look at this like overall right side, we take the equality. And the reason why is that like the problems that we deal with are kind of like, you know, like what is the maximum angle or what is the maximum force needed at which an object will not slip. So this means that if I exert a little bit more force, then I'm overcoming static friction and now the object is moving. Make sense? Awesome. And now kinetic friction is very similar, same form, we just have a different coefficient. Okay, another type of force is drag force, air resistance, resistive force. So, you know, drag force and air resistance are kind of the main like terminology you'll hear, and this generally depends on velocity. So if you have a car moving really slowly, there's hardly any like air resistance, but if you have a car moving really fast, then it's there's more of a drag force, there's more air resistance. So it's, you know, dependent on velocity. It also acts opposite to the direction of velocity. So what this is saying is that, like, you know, if you have like a hill over here, right, and then you have a car that's moving down the hill. Imagine it's a nice car. It's moving down the hill. Now, what direction is the drag force or is the air resistance going to act? Well, it's gonna look something like this here. And the reason why, the way you can remember this is that, you know, if it were acting in your direction, then you'll be going faster and faster. You can imagine this was a straight, you know, surface, and if air resistance was going in your direction for some reason, then you'll just keep constantly speed up and up and up. So it goes opposite. And yeah, and the types of problems we'll see this in is like an object in free fall experiences drag proportional to velocity, ding ding ding, know what to do, and find terminal velocity. So the reason why we have terminal velocity is because at some point the force of resistance is so strong that you can't go anymore. So strong that the gravitational vector, which points downwards, if you look at like the x component, which is, you know, this here, it's, you know, it's always constant, but, you know, the air resistance will increase, and at some point it's going to be equal to your force in the x direction. And at that point, your air resistance and your force going downwards is going to be equal, and that's your terminal velocity. And yep, like we said earlier, gravitational force or weight is just mass times gravitational constant. All right, let's look at some calculus. So this problem is, you know, pretty straightforward, I think. It's gonna help us review separation of variables. So we want to derive a differential equation for an object in motion subject to air resistance that is proportional to an object's velocity. Okay, so what we can start by doing is, you know, we can right away write that the air resistance is equal to F, right, is equal to minus some constant times velocity. And the reason why we have this constant is that this is the constant of proportionality. So we know that if velocity goes up, we know the force goes up, but we don't know at what rate. So the K is kind of going to encapsulate that. So this is always, we should write down proportionality constant. Okay, but the thing is, we want to derive a differential equation for an object in motion. Okay, an object in motion, so we want velocity, but normally F equals ma, you know, is acceleration. So what we're going to end up doing is we're going to say A, acceleration, is dv dt, the derivative of velocity with respect to time. Okay, so now what are we going to do? Yeah, we've introduced our proportionality constants. Now we can set them equal. So we can say m times dv dt is equal to minus kv. Okay. So this is from the previous slide. And now we're going to actually do the separation of variables. So we're going to put each variable in differential form and differential on its own side. So we're solving for v here. So we want to have this dv term, and we want the v term on the same side. So you can see over here we have dv divided by v, we brought this over, is equal to minus k divide both sides by m, and then multiply both sides by dt. So we got this equation here. And now we want to figure out, okay, how do we solve for v? Well, we take the integral, right? We want to get rid of the dv term. So we take the integral, and the integral of 1 over v, right, is natural log of v. So we get natural log of v is equal to minus k over m times t, because when we I can write this out here. So if we integrate both sides, we get ln of v is equal to the integral of minus k over m dt. And the integral of minus k over m dt, this is just a constant, right? This doesn't change with time. K is a constant proportionality, it's fixed, and m is also fixed. So we can take that out of the integral. So we get minus k over m times the integral of dt, which is minus k over mt. And of course, we don't forget the plus c over here. So we get this equation. And now we can simply take the exponential of both sides. So we get this over here, where we take the exponential of both sides. Oh, but then, you know, we always have the trick where e to the a plus b is equal to e to the a times e to the b. So that's what we've done here. We basically have this term here, and we also have this plus c that we could take out the exponential using this trick over here. And then e to the c itself is a constant, so we can rename that term as c0, another constant, and then we're left with this here. So you can see that the velocity itself over time, right? If you think about it, if you take t to infinity, right, then what happens? Think about that. With take t to infinity, what happens? We'll come back to that probably in another problem. So at time t equal to 0, what happens? The object in free fall has a velocity of 1 meter per second. This is a continuation of this problem here. We're just going to give more information now. So that was part 1. Now we're going to say that at time t equal to 0, the object in free fall has velocity 1 meter per second. So from the previous slide, we have this equation. And now we want to substitute in our known fact. You can think of it as an initial condition that v of 0 is equal to, we substitute in 0, and then, you know, e to the power of 0 is 1. All right, so you end up getting c0 is equal to 1. So this term here goes to 1. So you get c0 is equal to 1 when you simplify. So the final expression now we can substitute in c0 is this here, and this equation is only valid if at time t equals 0, the velocity is 1. If the velocity were something else, you have a different initial condition, you get a different constant up here. Okay, so now we're going to transition a little bit onto traditional Newton's laws. So the way that we want to attack these kind of questions now is we want to draw free body diagrams. So what this means is that we're going to have some kind of situation with some kind of like object and different forces acting on the object, and we want to create a very simple diagram that encapsulates all different forces on the object. And we're only right now interested in the external forces that act on the object. We don't want to consider any internal forces in the system. So we'll be doing these things in like other units, but right now we're only looking at external forces. And a few things to remember is that gravity acts at the center of mass. So right now everything is a point particle. We haven't looked at like, you know, actual bodies in motion. We're looking at point particles, so this is fine. And a normal force is a force by a surface that acts on the object. So the normal force, remember earlier we said, you know, an object on a table, you know, the object is sitting on a table, so there's a weight component, there's a weight vector, you know, pointing downwards. But then due to Newton's third law, there's also a normal force that's pointing upwards, which is the force by the surface of the table that's acting on the box. And yeah, we can right now we can neglect the mass of like ropes, strings and cables, like all those things. We can just say that they're negligible. And yeah, one key thing is that So we're going to label all forces in their directions, but if the direction is incorrect, it's totally fine, because what's going to happen is that we'll end up getting a minus sign. So if for some reason we have a force and we do the math and we come up with like minus 4 newtons, that means that our magnitude is 4 newtons, but our direction was actually opposite than what we thought. So we would just flip the vector, and if you were to actually resolve it, you would get 4 newtons. So just a little thing to keep in mind. Also, we want to categorize the sum of forces. So in these types of problems, there's mainly 2 situations, right? So either the sum of forces is 0 or it's not 0. So if it's 0, we have equilibrium situation, nice easy to solve for. If it's not 0, then we have the sum of forces is equal to mass times acceleration. And in this case, we have to kind of use what's given, and then we have to use this F equals ma to come up with an expression. And oftentimes, the forces in one direction will be 0, and the forces in another direction will be non-zero. So there we have 2 kind of situations where we can use one case to solve for given quantities and substitute it in. And the last but not least, if there's multiple objects, you should draw separate free body diagrams for each one. Okay, so I came up with a very brief checklist. I guess it's not super brief actually, but I came up with a checklist that kind of, this is kind of how I would approach a problem if I'm thinking about all the different types of forces that might exist. So the first thing I think about is gravity. So gravity, points downwards to the center of the Earth. Even if an object is on an incline, it's not the biggest misconception. Like if an object is over here on an incline, it's not going to point like that. That's a big no-no. It's not going to do that. It's actually going to point. It's actually going to point straight down. The object, the gravitational vector is going to point straight down towards the center of the Earth. You can decompose that into different components, however you want to. Like you can do whatever you want, but as long as the resulting gravitational vector points downwards, you're in good shape. Normal force, any kind of contact with the surface. Usually if there's like a perpendicular kind of surface, like an object at a corner, this kind of situation here, where you have a corner and then you have an object that's kind of placed over here, then you would have a normal force here and probably a normal force here. It's a surface force. And these you usually solve for by looking at equilibrium conditions. Okay, frictional force is the next one. So I think, okay, the object is in motion, if it's on a surface, and if we're given a coefficient of friction, for example, then we know what to do. There's a frictional force, but I think about frictional force, and I think about what kind of frictional force. Is it static or is it kinetic? So if the object is stationary and then it starts to move, then it's a static coefficient that we use. If it's an object that's moving and it's still moving when we're analyzing the problem, we're not moving it from rest, we're moving it from already in motion, then it's kinetic coefficient. We use the kinetic coefficient of friction. So oftentimes you might see a problem that gives you both static and kinetic, and it's up to you to decide which one to do, and this is the thought process that you should have. Is it going from at rest or is it going from at motion? Tension, so any type of taut rope, is tension, and the direction, the direction of the force vector will be parallel to the rope. Air resistance, only if the problem states. If the problem doesn't state anything, then you can safely assume that there's no air resistance, and this acts opposite to the velocity vector. Contact force, so this is kind of like a true external force, if somebody's kicking a ball, or if there's an initial force that's applied to a system, those kind of things. They're usually explicitly said. So it's an exterior contact force. Look for those too. And there's something called impulse, which we'll look at in a later unit. This is a force over a period of time, and kind of delivering force. We won't really see that today, but it's just something to start to think about. All right. So, just a little bit more on the topic of friction. So, when an object, is in motion on a surface, we need to figure out, like, we kind of know already how to do, like, how to figure out if it's static or kinetic friction. But now we kind of have to think of like the direction of friction. So, if an object is against a wall, the friction vector, is parallel to the wall. If it's against a corner, like we saw, in this diagram with normal force, there'll be two frictional forces depending on how the object is moving. In general, like the frictional force will go opposite to the direction of motion. So here, the object is moving this way, so the frictional force is going to go this way. You can imagine like the surface doesn't want the object to move, kind of. So it's kind of like, it's a rough surface, doesn't really want the object to move, so it's opposing it. But yeah, when in doubt, you could label the frictional force this way if you wanted to. But when you do the sum of forces, you would get like kind of like some gravitational force. If we call this here the x direction, we would have some kind of gravitational force here. And if for some reason you say like, oh, Fs is this way here, you would get plus Fs equals 0. And then you could see like you would end up with a minus sign here. So you know that the direction is wrong, but your magnitude is correct. All right, so let's look at a practice problem, which this was an actual AP question. So a skier of mass m is skiing down a frictionless hill, okay, it's frictionless, that makes an angle theta with the horizontal as shown in the diagram. The skater starts from rest at time t equal to 0 and is subjected to a velocity-dependent drag force due to air resistance of the form F equals minus bv, where v is the velocity, b is a constant. Okay, so a few things to pick up here. Frictionless, angle theta with the horizontal. I'm seeing that, the skier starts from rest at time t equal to 0. That's an initial condition to me. At time t equal to 0, the velocity is 0. And also there's an external, or there's an air resistance force that we have to keep in mind. Okay, so on the dot below, that represents the skier. We're going to draw a free body diagram. Okay, free body diagram. So what we're going to do is we're going to go through the checklist. And because these slides aren't animated, it's already showing the answer, but let's take a look. So is there gravity? Well, yeah, we're on Earth, right? So there's going to be gravity. And the gravitational vector points straight down into the direction of the Earth. Do we have a normal force? Yeah, we do. We have a surface here, right? So we have a kind of like a surface force. We have a normal force that's basically opposing the y component of gravity. So we have a normal force. We'll look at that later. Do we have a frictional force? Ooh, no we don't, because it's a frictionless hill. Do we have any tension? No, there's no rope or string in this question. We do have air resistance, right? We have a drag force here that goes opposite the direction of velocity. Do we have any contact forces? Like, do we have any, buddy kicking the skier? Do we have any initial force? No, we don't. And no impulse. Okay, so I think we're good. I think this is our free body diagram. Let's see. So that was part A. Part B, okay. Write a differential equation that can be used to solve for the velocity as a function of time. This is very similar to the question that we did earlier. A little bit different there. So the word differential equation and velocity, right, is kind of reminiscent, like, if you think of velocity in differential form, you think of this here, acceleration is the derivative. So we can use F equals ma, but how do we do this? So the normal way that we do this is we introduce a tilted coordinate axis. Okay, so what does this mean? This means that normally like our coordinate axis is like this here. We have x and y. But in this question, it makes more sense to tilt the axis. So if this is the hill here, we call this our x direction now. And we call this here our y direction here. And the reason why is that our velocity is along now the x direction, and the y direction is just going to be perpendicular to the x direction. So Okay, cool. So there's no velocity in the y direction. So the acceleration is 0 and the forces are balanced. This is important. We tilted the coordinate axis, and now we know that is the skier moving perpendicular to the cliff at all? The skier is not, because if the skier were, then the skier would experience a force that's like upwards, right? It would be motion in that direction, and there isn't any. So there's no velocity in the y direction, right? The acceleration is 0, and the forces are balanced. So we have one axis. If we go back to earlier, we have in one direction we have the forces is 0. However, there is acceleration in the x direction, so we can apply F equal ma there. Okay, so I just want to pause for a second and like go back over here, just like the overall tips. So we said that we want to categorize the sum of forces, and what I said was that either we have the sum of forces as 0 or the sum of forces is not 0. And in this case, in the y direction, the sum of the forces is 0. And here in the x direction, the sum of the forces is non-zero. So this is a really good situation because we can solve for forces in one direction, substitute it in, and that's what we're going to probably end up doing. Okay, so what are the sum of the forces in the x direction? Well, we have mg sine theta. So this is the x component of gravity. Okay, so because we tilted our coordinate system, I'm just going to redraw it a little bit bigger over here. Okay, so the skier is not going to be a point particle, and our gravitational vector points down, but because our axis is this here, we want to look at the component of this vector along the x direction, which is just, if we draw this kind of thing here, it's simply, this component, which is, and this theta here is the same thing as this theta. You can work that out geometrically. So we take the sine to get this here. So we get mg sine theta minus bv. So this comes from the fact that our drag force is opposite. Like over here, our air resistance is opposite. So basically, it's this component of gravity minus the air resistance is equal to our acceleration, m times dv dt. And once we figured this out, now the next part of the question is determine an expression for the terminal velocity. So what is the terminal velocity? It's, it's the fastest a skier can ever travel. And at terminal velocity, your velocity is not changing. It's terminal. It doesn't change at all. And this means that the acceleration is going to be 0, because acceleration is the change in velocity. So what we can do is we can just set, okay, we'll just set this term here equal to 0, and then we get we get this equation. We just set the right side to 0, and then if you solve for vt, you end up getting this here. So this is our terminal velocity equation. And think about it. So in the problem, we know that at time t equal to 0, the velocity is 0, and now we know that at t equal to infinity, that the velocity is this. So we have an initial condition and we have a final condition at the very end. All right, part D. So now we want to solve the differential equation in part B to determine the velocity as a function of time. Okay, so why wasn't this question asked before C? And the reason why is that we needed that initial and final condition. Remember, oftentimes we have some constant. We have to solve for the constant using initial conditions. So part C gave us that constant. So now I bet you that we're going to come up with some constant. So let's take a look. So this equation here comes from earlier. So if you take this equation and rearrange it, oops, I'm going to copy this I'm going to paste it over here. Yeah, if you take this equation and then you you rearrange it, like you get this term in the numerator, and this mg is this part here in the denominator, and then you put this on the other side, take the reciprocal, multiply it to the other side. Yeah, you end up getting this here, and this is basically our separation of variables. We want dv, which is on one, our velocity differential, and we want the dt to be on separate sides, and we want all terms that relate to that vary with that to be on the respective side. So in this case, m is a constant, so it can be basically wherever you want it to be, but mg sine theta, that's also a constant, but this minus bv is a velocity dependent term because there's a v in it, so we want it to be on the dv side. Okay, now we need to make a u substitution, so this is just from calculus. We let u equal to this part here, and then we take the derivative, so we get du is equal to minus b times dv. So this term here goes to 0 because there's no v in it, so you should end up getting minus b. And now we can substitute in, so we substitute this into this left hand side, so we end up getting minus 1 over b times du divided by the denominator, which is u. And the right side we keep it the same, and now we want to integrate both sides. So if we take the integral on both sides over here, we get something very similar. So the minus 1 over b is a constant, so this term here is a constant. It comes out the integral of du over u is the natural log of u, and then the right side here, well, 1 over m is a constant, so we can take that out of the integral, and the integral of dt is just t, so we get t over m plus c, plus a constant. So this is a constant from that I was mentioning earlier. So now I want to solve for u, so we get, we can solve both sides for u, multiply by this, and then exponentiate, and clean it up by extracting out this as another constant like we did earlier, so we end up getting this here. But now we want to substitute back in, so we solve for this thing here. We want to substitute back in u, so we get this here, and now we have an expression. We haven't explicitly solved for v, but we can. To make things easy, we're going to use our initial condition right now. So we'll use our t equal to 0, v equal to 0 condition. And the reason why we're doing this is because the terminal velocity condition is like technically a t equal to a long time, which is a little bit difficult to work with, because if you send t to infinity, this term here will go to infinity. So instead we use t equal to 0, v equal to 0. And what do we get? Well, we put 0 here, so we end up getting, this term stays the same, but our v is equal to 0, so this term will drop, and then this term here will go to 1 because e to the power of 0 is 1. So you end up getting c is equal to this. And now you can do the algebra, and you end up if you substitute c back in and you solve for v, you end up getting this expression here for v. And a quick check is that we said that terminal velocity is the fastest you'll ever go. So at t equal to infinity, this term here goes to 0, and you end up getting mg sine theta over b, which is the same thing here, mg sine theta over b. So that's a quick check. Awesome. So yeah, so now we're going to look now at centripetal force. So I'll take, if there's any questions, you can put them in the chat. All right, no questions. Okay, awesome. So let's look at centripetal force now. So centripetal force. So I want you to think of a yo-yo traveling in a circular motion. And I wish I had a yo-yo here to demonstrate, but imagination will suffice right now. And you can think that at different timestamps, the velocity vectors have the same direction, have the same magnitude. The same magnitude, and the directions are the only thing that's changing. and they're all tangent to the surface, to the circle. And the reason why is that, imagine for a second, the yo-yo is spinning in a loop like this, and you were to cut the string. What would happen? The yo-yo would just start flying out at a path that's tangent to the circle. So in this case here, this is the center, and if you were to let go, if you were to cut the rope here, the yo-yo would fly out at a tangent to the path of the circle. So that's a velocity vector. And one thing that they never really I feel like a lot of textbooks don't really ever mention this, is that this is why centripetal force points towards the center. So if you think of two velocity vectors like this, we have a green one and we have a red one, and we want to find the change in velocity, which is the acceleration. We can simply subtract the two vectors. So we can take green minus red. So acceleration, which is about the change in velocity, is equal to the green vector minus the red vector, which is the same thing, of course, as green plus minus 1 times the red. And if we minus 1 times the red, it's just changing the direction, not the magnitude. Magnitude's still the same, so we can flip the vector. And then if we were to add these two vectors, like this over here, we put the tail at the head of the other one, and we add the two vectors, we get a vector pointing downward. So the change in velocity is equal to this brown vector here. That's the change in velocity. Okay, so centripetal force, and remember the change in velocity is acceleration. So we have acceleration pointing towards the center now, and you can repeat this to every step on every step of the path. You'll see the same thing, it points towards the center. Centripetal force is a force that causes an object to move in a circle. So change in velocity is acceleration. If there's an acceleration, there's a force, and we call it centripetal force. It's the force that causes the circular motion. So for a yo-yo, this is the tension in a string. For a car making a turn, a banked turn is, you can think of on a racetrack, the track is a little bit tilted, so that the car is going to be moving in a circular form, but it's not going to be traveling straight on the ground. It's going to be traveling a little bit at an angle. Friction is providing that inward force, but it's not like a external force. It's just like a force that's you have to look at the problem, you have to figure out what's causing the circular motion, and you can call that force a centripetal force. So how do you spot this? Well, if an object is moving in a circle at constant speed, that tells you right away, probably centripetal force question. Car making a bank turn, usually a centripetal force question. A ball and a string is spun in a circle, centripetal force. The word circle, constant speed, moving, circular motion, centripetal force. All right, practice problem. Okay, so, and I made this diagram, so I hope it's nice. It took a while. The Gravitron is an amusement park ride that resembles a flying saucer. A rider is strapped to a tilted tile that slides up and down when the saucer gets to its top speed. So basically, you're sitting here on this little tile, and as you go faster and faster, the tile starts to move up a little bit. If you slow down, it'll fall back down. It's not stuck to the ride exactly. If the radius of the saucer is r, so here is r, and the tile makes angle theta with the vertical, how fast must the saucer spin for the tile to just start to slide up against the wall? Between the tiles and the wall, the coefficient of static friction is mu s. The coefficient of kinetic friction is mu k. Okay, so just think about the question for a second. For the people watching live, let's give it a second to digest the question. Okay, so in this problem, we have this rotating contraption here. like this thing here is kind of spinning in a circle. This is the center of the circle, radius r, and you have a guy over here that's just kind of lying down on this tile, and as you start to spin, the tile will start to slide up, and we're given friction, we're given a radius, circular motion, angle over here, probably some forces like a normal force is involved. I think, and the other key thing that we have to remember for centripetal force from physics 1 is that the centripetal force is mv squared over r. So this is a centripetal force question. I think the way that I would approach this problem, like without getting directly into the solution, is that we want to figure out how fast must the saucer spin. So I remember this formula, right? This is our go-to centripetal force formula. I want to kind of solve for v, but I'm given m and r, but I'm not given what the force is. And the way I would solve for the force is I know the direction is going to be towards the center, right? The centripetal force will be towards the center of rotation, but I don't have I don't have any forces labeled. I don't have a free body diagram, so I can't do it just yet. But what I would like to do is I would like to come up with some expression to come up with the sum of forces in this direction here, and then it's just plugging it into this formula. We should be good. All right. So let's draw a free body diagram. So this is our diagram here, and I'm just copying and pasting it. This is the checklist from earlier, and let's get started. So is there any gravity? Well, we're on Earth, so there is gravity. And gravity is pointing downward. It's not pointing upwards. It's not pointing like down here, up here. No. It's pointing directly downwards. Is there a normal force? Well, there is a surface, and the surface is pressing up against the person. I would hope it is. So the normal force is perpendicular to the surface. So it doesn't look super perpendicular, but I promise it is. This is the normal force here. And now, is there a frictional force? Okay, so this is a little tricky. There is a frictional force, but what direction is it? And of course we can mess it up. We can put it like in the wrong direction. We'll end up getting the right answer somehow, off by a minus sign. But let's think about it. Well, when you start to spin, where are you gonna fly? Are you gonna move downwards or are you gonna move upwards? Well, I would probably imagine moving upwards, right? I would imagine flying out, flying out of the ride, basically upwards. So if you're flying out of the ride, like upwards, if that's your direction of motion, friction is going to oppose that. So friction is going to actually point opposite your direction of motion. You have to also think about, what type of friction is this? Is this kinetic or is it static friction? Well, if you remember, I remember we said that static friction is when you go from at rest to then in motion, versus kinetic friction, which is motion and you're still going in motion. So in this case, we're at rest initially, and then we're going to go and move in some kind of we'll have some kind of speed. So because we're going at rest to in motion, we have to use static friction. And we're given both, so to be aware for the tricks. Yeah, and there's no tension, there's no air resistance or external, no kicking a ball or anything like that, and there's no impulse. So we pretty much just have these forces. Okay, so just to conceptualize this a little more before we, the next slide is gonna start to bring out the math. When the person starts to slide up, once the centripetal force is equal to the frictional force. So the centripetal force is going this way here, and the frictional force, well, a certain component of the frictional force, like the true barrier in this question of motion is the friction itself, kind of. That's like the main force involved. once you kind of start to overcome, if you were on ice, you would slide out right away. If you were like on carpet, it would take a little bit more force. So once you start to overcome that, that's when you start to move. So when the gravitron rotates slowly, the centripetal force is really small. So you're still kind of stuck on the ride. But at some point, you're going to overcome that barrier and you're going to end up moving. So what is the centripetal force? So we said, imagine you're a particle, you're traveling in motion. The acceleration is pointing inwards, right? Because your velocity is constantly tangent to the circular path that you're making. The acceleration will point towards the center, so it'll point over here. And it needs to point the same direction of velocity. And right, the centripetal force is not another force, it's just made up of our existing forces. Okay, so now the centripetal force, and in this diagram we kind of broke up, it up like our existing forces. So we normally, we have our normal force that's pointing this way, we have gravity that's pointing this way, Fn, and we have our frictional force, which is pointing this way. And now we're just saying that we want to use our tilted coordinate system. So we want this to be our x-axis now, and we want this here to be our y-axis now. Which direction? Well, this could be our plus y, and our plus x. We could either choose it to be here, or we could choose it here, and we'll see which one's more convenient as when we start writing down expressions. But basically, we want to decompose these, the Fn doesn't really work nicely in our coordinate system right now, it kind of looks like that, and same with our Fg, doesn't really look so well, but our frictional force is along an axis. We want to basically project our vectors onto the axis. So Fn will look like, this over here, plus this vector here, Fnx, Fny, and Fg will have a vector here, plus a vector here, so Fgx and Fgy. And if you add up these two vectors, you end up getting Fg, so we're good. And same thing here. So what's the forces pointing inwards? Well, I see gravity is one, and I also see a frictional force. Yep. So we went over this. The horizontal now, our centripetal force is pointing in the center. So we have, we can break it up like this also, along our, centripetal force axis and vertically, and we can also break up our vectors along this axis here. So these are, two options. Okay, so what we're going to do now, because this is a centripetal force question, is we're going to go with our non-aligned axis. So earlier, in a normal problem, we would look at what basically I described over here. We would look at this case here, where we use our tilted coordinate axis. But in this case, because our centripetal force is kind of also non-aligned, the easiest way is to basically go with the normal axis. Like our normal meaning our x and y looking like this here. Okay, so what are some of the forces in the x direction? So in this case here, we have a normal force that's pointing this way. Our x component is going to be the normal force times the cosine of theta. So this angle is equal to this angle. So we get this term. And for gravity, which points downwards, our x component is going to be the sine of theta. So we get this term. Does it equal 0 though? I don't think so, right? Because if it were to equal 0, there's no motion, but when it starts to slip, that's when we actually have motion, so sine equal to 0. How about some of the forces in the y direction? Well, we have we have our normal force, we have the y component, which is the sine. We have gravity, And we have our frictional force. So gravity points downwards, and our frictional force. So earlier here, I think I misspoke. This is our frictional force, of course. It's this component is the x component of the frictional force, and this here is the y component of the frictional force. Gravity is only present, of course, in this direction. And because there's no motion in the y direction, it's equal to the sum of the forces is 0. So, yeah. So a key thing is like, you can imagine like you're moving in a circle like this over here. So their center, our center's over here. If this were like a yo-yo kind of thing, in a string instead, you could imagine, it's like you're traveling in a circle here. There's no motion in the vertical direction though. Like you're only moving in the horizontal direction. So even though like in this problem here it looks like you're slipping upwards, like you're at the moment that you start to slip, it'll be like it won't be vertically. It'll be just like your centripetal force is in your x direction, so your slipping won't be vertically. So some of the forces here, some of the forces in the y direction here, we can rearrange it. So what is the frictional force? Well, here it's just mu s times the cosine. The frictional force is like mu times the normal force, Fn, but it's mu s, right? And over here we have the same thing, so we have mu s times Fn, and we can solve for Fn in the second equation here. So this Fn comes from this equation here, and if we rearrange it, we end up getting this expression. So we have an expression for our normal force. Okay, I'll just paste it over here just to remember. And now the sum of the forces in the x direction is the centripetal force. So Fx is equal to mv squared over r. And if we plug in, we get, and we're plugging in, by the way, this here. We're plugging in the sum of the forces in the x direction, and we say that's equal to mv squared over r. Okay, now what we're going to do is we're going to substitute in our expression for our normal force. That's the only term that we don't know, so we can factor it out over here, and we can substitute it in. And basically, now we have an expression where we know what m is, we know what g is, we're given our constants, our coefficients of friction, we know what theta is, and our right side, well, we're solving for v, and we know what r is. And if we solve everything, if we rearrange all these terms here and multiply by r over m, we end up getting this as our expression. So this is the velocity. This is like the speed that you need to be traveling at to start to slip. So anything less than this speed, your centripetal force is like weak. Like your force that'll like move you from your seat won't actually move you because it's not strong enough. But once you travel this fast and your centripetal force is really big, and that's when you start to move. And those are all the problems for today. I'll still be online for a few minutes if there's any questions. Thank you all for coming.